proving that geometry is very general and information theory could find also geometrical concept and so on. And the next presenter is Rafael Oliveira, and the author is Marcelo, and you see the title and also the other things. Please take your presentation.
Okay. So it's working? Yeah, okay. So what I'm working with is a geometrical approach in information theory. To talk about this, I have to give a little basics of information theory. If not, it will make no sense, the presentation. So let's get to it. In 1948, Claude Shannon, he published his paper, A Mathematical Theory of Communication, where he gives this basic model and which has been used for various applications in communications, where you have an information source which produces some message. You have a transmitter which encodes the message. You have the channel over which the message is sent. A receiver decodes the message, and the message goes to the destination, and if everything went well from the beginning to the end, the destination should receive what was sent initially. So in coding theory, we work exactly with something called a noisy channel. So you have your transmitter, someone is sending something, and the channel puts some noise into it. So what that means is that you have a set of messages that are sent through the channel, and you have a set of messages which are received on the other side. And these things, they're very general. They can be images, they can be numbers, you can see them as you want. And the important thing is that the channel is modeled by a probability matrix. What does it mean? Here in this matrix, we see here that when the transmitter sends an x1, there's an 80% chance that a y1 will be received, a 15% chance that a y2 will be received, a 5% chance that a y3 will be received, and so on. So this matrix, it characterizes how the channel behaves with respect to what I put in and what comes out. And the whole point here is how do you communicate, how do you send things through this type of channel. This is very general. Many problems can be seen as not necessarily related to communications, can be seen as things like this. You have applications in finances, you have applications in many types of places. So it is common in communications for you to take the sets to be just binary words, ones and zeros, because that's what computers do. So it's the usual thing to be done. So in coding theory, what is coding theory? Coding theory is the following. What happens? When you have a channel, let's say that generally the decoding is done in the following. If I receive a y1, I assume that x1 was sent, because it's the most probable to have been sent. When you look at this column, it's the highest number here to have been sent, and send things for each one of these. So a y2 will assume that an x2 was sent, a y3 will assume that an x3 was sent, and these red guys, they represent when there has been an error in the decoding, let's say. If I send an x1 and this is received, it's an error, and with this you can calculate the probability of an error, let's say for this here is at 23%. With this type of channel, if you want to, you can make it better. So what is coding? Coding is a restriction. You say, I'm not going to send everything, I'm going to send less things, so that I can permit some sort of leeway for error. So how does this work? This works in the following. Let's say that if I take the code to be, I only send x1 and x3. That means I'll never send x2. That means that when a y1 is received, it will be decoded as an x1. When a y2 is received, it will be decoded also as an x1. And so you end up with these red guys as the mistakes, and you get a lower error. But you only send 2 symbols instead of 3. So the whole area of coding theory has this problem about how you're going to work with these things. Like You want, at the same time, you want to lower your probability of error, but you want to send as much as you can. And a lot can be said about this. An example of a channel that is very much studied is the binary symmetric channel. It's just when you send a 0, there's a probability p of getting a mistake, and the same for when you send a 1, and 1 minus p for it to be correct. This channel is the most widely used channel in information theory. Probably, I don't know, 90% of everything is done with this type of channel. And one of the reasons for it is actually a symmetry reason. It's because when you don't know anything about the channel, this is the best assumption that you can make about the channel. It's the maximum entropy assumption. It's the symmetric assumption, as the same as when in probability theory, when you don't know the probability, this Laplace criteria of getting the same chances for the events, it's the same type of thing here. So when you start to take blocks of messages, so you know that when you send a 0, this is the chance of receiving a 0. So when you send 2 zeros, this is the chance of receiving 2 zeros. When you send a 0 and a 1, this is the chance of receiving a 1 and a 0. You end up with this type of matrix. And in general, for these blocks, you end up with these terms which are a probability to the power of d, 1 minus p to n minus d. And the thing that happens here is that where this d, this number d here, it controls the number of mistakes that were done in what was sent. And this number of mistakes actually can characterize a distance function between your words. And it's what's called how do you say, a Hamming distance. So the Hamming distance, if you look at your binary words between, it's just the number of entries in which they differ. And the Hamming distance, it's defined on the Hamming cube, so you have your square, cube, hypercube, and bigger dimensions. And the number of different entries is the same as also if you look at the graph of the cube. It's just the distance by counting how many edges you need, the shortest path distance in the graph. And the point here is that this distance here, it coincides with this d here, and it means that for you to decode for that channel is equivalent to decoding using this distance. So that means that the channel is matched to the Hamming distance. And with distances, you can get a geometrical theory. This gives you a geometrical theory for decoding, and it's what's done in most of information theory. And you use this Hamming distance for all kinds of things. You can define things like perfect codes, or do all types of geometrical things. And the important thing here is the following, is that the binary symmetric channel is matched to the Hamming distance. And this, since the binary symmetric channel is, let's say, the most studied of the channels, this explains very well why the success of the Hamming distance, if you look at information theory, like I said, 90% of things are going to be done with the Hamming distance. Not many other distances are considered. So what I'm working with is looking at channels in general. So the first question that you can have is, when is a channel in general metrizable? When can you do the same things for different channels? Because in many applications, you have different types of channels. In most real-world applications, the channels will not be necessarily a binary symmetric one. And if you can find a metric for your channel, you will have access to all these geometrical tools for making better codes, as is done with the Hamming metric. Well, as I just said. So many things to discuss and not much time. I could talk about channel metrization, the space of channels, the space of distances, and then Hamming cube embeddings. I'm going to try to talk about channel metrization and maybe a little bit of space of distances, and comment on the others if time permits. So the question of channel metrization, that is for which channels you have a metric, and so for which channels you can build this geometric theory. it goes back to Massey in '67. You then have some results here, which I leave in the references, in terms of certain channels. And in one of our works, we fixed the channel, we gave an algorithm which finds if it has a metric or not for it. So we solve it for a fixed channel, we give a polynomial time algorithm. It doesn't work, I mean, it's still an open problem to do it for many families of channels, but for a fixed one, if you have a particular application, we can find a metric for you. The way that it works, so here it's just to give a taste of how it works, is sort of if you have something like the following channel, you can construct a graph, a directed graph out of it, and metrization or not is going to depend if you can find some type of cycle in the graph. If there is a cycle, it will not be metrizable. So this is just to show you, you can transform it into a sort of graph theoretical approach. So what I'll talk about here now is about the space of distances, because then I can talk a little bit about the space of channels. So distance here, we're going to work in general with semi-metrics. It satisfies these properties. Distance from the point to itself is 0, it has to be symmetric, and it's only 0 when the points are equal. And it's generally, we work also with translation invariant distances. I'll explain why a bit. So the notion that we use is that two distances, what we look at is at the space of all distances. So you take the set of all distances over a finite set n, and you put the following equivalence relation. You say that two distances are equivalent if they give the same decoding. And we look at the space of all these distances and see how does this equivalence partition the space? What is going to end up happening there? And what we get is, so if you look at the space of all translation invariant semi-metrics, it's going to be all matrices which are, symmetric, and actually they're going to be defined only by one single row. But the important concept here is that you can identify it with some Euclidean space. And the important thing here, I'm not going to, better for me to jump a bit, is the following. That if you, this is the following. If you look at this here represents the space of all translation invariant distances. It's going to be isomorphic to R3. For translation is over 4 points. If you get it over 4 points, it's going to be isomorphic to R3. And this is going to be the partition of it into the equivalence classes. This partition, it corresponds to a permutaedron. Its symmetric group is just the permutation group. The translation invariance, so what happens actually is the following. If you look at the space of all channels with these four symbols, it's going to be a 16-dimensional space. If you then look at what is the space of distances, it's going to be a hyperplane in this space. And the space of distances is going to cut this, this other space that we had, 16-dimensional. You're going to end up with a 6-dimensional space. And if you look at the translation invariant ones, it's going to be this 3-dimensional space. So the nice thing about this is that I can draw it. Because the next non-trivial case goes to 7 dimensions. So these things here, they're very high. They're very high dimensional to look at. The symmetry group for the translation invariant case has this nice permutaedron behavior. In general, it is not, it's going to be a product of these symmetry groups. And one of the things that we're working with is precisely characterizing how these symmetry groups work. Because a better understanding of this can give to rise, one of our goals is a rise of sort of an approximation theory for channels. That means that you have channels which have no distances, but you want to find what would be the distance which is closest to it. Because as I said, with distances you can use all types of geometrical tricks to make nice codes. And we want to bring this to channels which do not have this type of thing. apart from that, I'm not going to have time to go into this, so I'll leave it for questions. Thank you very much.
Nicely in time, please. Is there any question? Yeah, please. Nothing.
When you had the criteria for the metric space, the more general situation, when you had the
Are you talking about this, or?
when you first introduced the criteria for that, right there, yeah.
Yeah.
So there's also, if you multiply, if you think of x and y and as vectors,
Yeah.
if you multiply one of them by a scalar, then part of the requirements is that the scalar comes outside. Does that figure in at all in your?
So there's a big what do you say?
I turned this way.
So these definitions of what is a distance or metric, they vary a lot from place to place. Here I think I'm following the Encyclopedia of Distances one. In this one, it's just so what happens? I need a little bit more than a distance. Because without condition 3, it's what's known as a distance, just distance. With condition 3, you get a semi-metric. You can also have translation invariance, which will make it into a metric. But we don't need that much. You can show that in terms of decoding, the triangular inequality is not necessary. What you're talking about the multiplication, is about a norm. It's for a norm space that you're thinking about in terms of multiplication. Because in this space, as is, we don't have a multiplication.
Okay.
I mean, you could define one, but if you go just for binary, then there's only 2 elements, 0 and 1, so it's just going to trivially be right. If you go to other things, then I'd have to think about it in terms of like what could be said if we add, for example, a norm to, if we work not over the binaries but over FQ. It could be thought of, or a norm or some type of valuation, I don't know. Because it's going to be more structure, so it might be useful because all of these things that they give you more structure, if you can put them, they're good in terms of the code. When we're making a code, you try to like, for example, a linear code is sort of a translation invariance symmetry. So you always, the point of these codes being symmetric is for easy decoding. So everything that adds structure, it can help in terms of this, but it reduces the possibility of what you can do because you're being less general.
Once more question, please.
How that Bermuda-Hadron enters the picture?
So it's just that this cone here. So these cones, this is like a conic representation, but you can use the closed representation for this. This one corresponds to the Bermuda-Hadron. Here, each of the, it's in the following, so you have many cones here. You have 3-dimensional cones, 2-dimensional cones, 1-dimensional cones. The 3-dimensional cones, they're going to correspond to permutations like, the 3-dimensional cones are going to correspond, you're going to have n factorial of them corresponding to each permutation. The 2-dimensional cones, they're going to have permutations, but this comes from weak orderings. So in weak orderings, you allow some equalities. So you're going to have permutations, but with some equalities inside. So the number of them is going to be a Stirling number. N choose k, but Stirling at the second type. And then the same for the other ones. So if you look at this in the how do you say, the closed, I don't remember the name, but it's like in how do you say, in linear programming, you have these 2 ways of representing the same type. If you look at it in the closed form, it's going to give you a Bermuda-Hadron, where the faces are going to be the three-dimensional ones, the lines are going to be the two, and the points are going to be corresponding to the ones. So you can mix it on. In terms of the permutation group, it's going to behave the same.
Thank you. Please, we thanks the
Thank you very much.
Then I will be again the presenter, then we will come.
I will go up and get him ready.
Please. Please, your
Yes, I'm getting ready.
Yeah, it's here.
here.
It's here.
Yes.
Please.
Here's your USB, don't forget it.
This is after there is a pointer.
No pointer.
No pointer.
Pointer.
Finger.
No, I can show you how to point.
Yes. Please.
So you see the cursor here? You see that? Okay, this will change your slide. You see on the screen over there? What you'll look this is what's on the screen. This is what's next. This comes next. That's the
Next is
this is your next slide.
yeah, next.
But you only see this on the screen. Now when you want to
Click.
click, you see this? Click here.
Yeah.
And now this slide is on the screen.
Yeah.
And this is your next thing.
Yes.
And
And
if you-
always click the next slide.
You will be clicking over here.
Only the here.